Hello everyone. Lecture 10. So we're going to continue this discussion that started last week, and it's essentially the general topic of linearity and equivalence. And we saw up to Thévenin and Norton equivalence and source transformation last time. And what we are going to see today, and I hope we can close this chapter today or get very close to it, in a way you might say is an extension to a large degree of the concepts we talked about. And I'll be moving maybe a little faster because some of these are not maybe as conceptually perhaps profound as linearity and Tavern and Norton equivalence themselves. You might view some of them as applications of these concepts. But there are still very important things here, some things that have broader implications than just circuits and electrical systems. And so there is a lot of depth still. But I think we can hopefully move a little faster. But I'd like to start with a quick reminder of Thévenin and Norton equivalence and how to transform one to the other, if anything, for us to all get on the same page. So we saw that a linear circuit, so a circuit that had linear resistors and linear dependent sources as well as independent sources, if you took such a circuit, looked at it between 2 points, 2 nodes, from the outside, you could essentially replace the whole thing with a Thévenin equivalent. And that would look like this. So a Thévenin equivalent is something like this. So you take your circuit and you replace it with its equivalent, which consists of an independent voltage source, V Thévenin, and a simple resistance in series with it, R Thévenin. And imagine your circuit was inside a box, and you're replacing what was inside with this. And recall that we essentially looked at the current voltage characteristics for such a circuit. And remember, the way I defined the current, I'll make this a little longer to make it easier to see. This is how I define the current, this direction. So when I draw the IV characteristics, keep in mind this is the way I've defined the current. If you define the current the other way, of course you have to reflect that on your current voltage characteristics. But the reason it's common to define it like this is that if you're looking at the effect of this circuit on something that you connect to it, you will immediately see that this source is trying to send a current in the direction that I've shown. So from a practical standpoint, it's useful to choose this direction for the current. And we saw that the current voltage characteristics looked like this. So you had the short circuit current here. And here you had the open circuit voltage. And this just happened to be V Thévenin, the voltage of that source. If you have an open circuit, namely if you don't connect this to anything other than a voltmeter, you will just measure the Thévenin voltage. And if you look at what current would make the voltage 0, or if you had a 0 volt drop here, namely if you had a short circuit here, what the current would be, you would see immediately that it would be V Thévenin divided by R Tavern. So these two parameters, V Thévenin and R Thévenin, obviously entirely define this, and that's a straight line. And to obtain the Thévenin equivalent of a circuit, we saw that you could essentially find any 2 points on this line, because to define a straight line, all you need is 2 points. But it is very convenient and perhaps insightful to find these 2 points. So if you have a big circuit, I think we looked at an example where you would, in one case, in practice measure or on paper calculate the voltage that you would see between those 2 points without connecting anything. In another case, you would add a wire there. You would measure or calculate the short circuit current. And from those parameters, you would directly have V Thévenin. And from the ratio of the two, you would get R Thévenin. And we also saw that you could do a similar reduced representation of a circuit in the Norton equivalent form. So Norton equivalent would be very similar, but it would use a current source, an independent current source. And that would be in parallel with a resistor. And you would call this R Norton. And this I Norton. And again, this is the circuit that you have inside the box, and you're concerned with its behavior from the outside. Notice again the way I have defined the voltage and current directions. And same as before, you can see readily that this circuit has current voltage characteristics in this manner. And that in this case, the short circuit current going through outside. So if you short circuit these 2 points, if you just connect them with a wire through which you measure the current, so if you put an ammeter there, you would immediately see that the voltage drop across the resistor is 0, and so all that current by KCL, all the IN current will go through the outside circuit. So your short circuit current is simply I sub n. And your open circuit voltage, so if you don't have anything connected here, all you're doing is looking at the voltage between those 2 points, which means you have a voltmeter. Well, the entire current goes through the resistor, so you have Rn IN as your open circuit voltage. So that's that point there. And we also said that from the outside point of view, these two circuits are entirely equivalent as long as you have the same resistor and that the Thévenin voltage is equal to Rn IN. So source transformation going from a Thévenin to a Norton equivalent, or vice versa. And all that required was this. And you can see that directly, that your V Thévenin should be Rn IN, and the two resistances should be equal. So I want to do a quick example of this. I don't think we did an example of how to apply this, how to use this. and then move on. So consider a circuit like this. Let's see, I have something here. So let's say this is 10 volts, this is 6 volts, 2 ohms, 2 ohms, 1 amp, 1 ohm. Find the current I. So this is the current going through this voltage source. But rather than trying to solve the circuit, going through all the KVLs and KCLs, see if you can use simplifications using the source transform method that we talked about, to see if you can simplify the circuit in a few steps and do it more easily that way. Okay, so find the current I using source transformation. Can you work on it on your own for a couple of minutes? So I want to use source transformation to do this. And my goal is ultimately to find this current in this in the branch that has the 10 volt resistor. Now, my problem would be a lot simpler if I just had one loop that had a few elements in it, and I could just write 1 KVL and find that current, right? So I'm going to try to see if I can get there by starting from a corner of the problem somewhere and see if I can simplify using the source transformation. So let's take a look at what we see here. If you take a look at what's inside this blue box, I think you would agree with me that this is already in the form of a Thévenin circuit, right? It has a voltage source in series with a resistor. If I converted this to a Norton equivalent, I'd end up with a current source here and a resistor in parallel with it, right? So between the 2 points outside this box, so between these 2 points, I'd end up having a current source and a resistor in parallel. And so then my left half of the circuit would look like a current source, a resistor in parallel with it, and then another resistor in parallel with it. And I realize we haven't yet formally talked about parallel resistors, and we'll do so today. But I think most of you are familiar with that from the past. And in any case, that's just a special case of a Thévenin circuit anyway. So let me convert this to a Norton equivalent and see what the circuit looks like. So I'll end up with a current source here, a resistor in parallel with it. Now, the resistor is going to be the same as the Thévenin resistance there. And the current source is going to be IN, which is VTH divided by RN. So in this case, it's going to be 6 divided by 2, which is 3 amps. So this is what I had inside that blue box. And if I change, or if I change from the Thévenin form to this Norton form inside the blue box, as far as outside that box is concerned, no one will be able to tell the difference. And that's why I'm allowed to do this. And so now the rest of the circuit, I have this other 2 ohm resistor here. And I have this 1 ohm, 1 amp. So I'm just simply drawing the rest. And remember that I'm interested in this current I. Okay. Now this box that I drew here, this was artificial. There isn't really a box, right? So I'll erase it. Now maybe you see things a little better. These two 2 ohm resistors are in parallel with each other. They have the same voltage drop between them. Maybe as a quick excursion, if I had something like this, what is the Thévenin equivalent of this? This is a quick side question. What is the Thévenin equivalent of this? 1 ohm between those 2 points. You can measure the or calculate the open circuit voltage. What is the open circuit voltage here? 0, right? If you just connect the voltmeter here, there's no source. You can measure the short circuit current. That's also 0. So how do you get the 2 ohms? The ratio of 0 by 0. That's simply telling you that the curve is going through 0. But you also need another point. Okay, in this case, the open circuit voltage and the short circuit current are the same. You need another point. But anyway, so we'll come back to this. But for now, maybe I'll invoke what you know from the past, that the combination of these 2 parallel resistors is 1 ohm. If you don't remember that, just take that from me for a moment. We'll see it in maybe 10 minutes. Okay, so the 2 parallel resistors that we have over there, I can now replace with a 1 ohm. And note that even though the circuit looks maybe a little different, you can always add more lines, more wires to make it look like what I just drew. Okay. So the next step from this then would be to just do that simplification. You still have the 3 amp circuit here. You have the 2 ohm and 2 ohm in parallel, which give you that 1 ohm. You still have your 1 amp here, and you still have this other 1 ohm there, and the rest of it. Now, what's another simplification I can do, or another source transformation? Now I have essentially a Norton circuit on the left-hand side, and another Norton circuit on top here. So I will now basically put the Thévenin equivalent of these 2. And that will give me a voltage source in series with a resistor, another voltage source in series with a resistor, and I have a voltage source. So I'll end up just with 1 loop going around. And that's basically what I'm hoping to get. Now, to make it maybe easier to see, I will just add a little bit of extra wire here. I'll bring this way. So if you look at my boxes now, I'm looking at this box and this box. So I have a Norton circuit, 3 amp and 1 ohm. If I want to convert that to a Thévenin circuit, I end up with a 1 ohm series resistance and I times R. That would be my Thévenin voltage. So I end up with this. So 3 times 1, which is 3 volts. Now notice one thing that's really crucial is the directions, the polarities, right? So for instance, going from this 6 volt, I had the plus side on top. I ended up with a current source going upward. Going back to what I had there, the two circuits that were equivalent, you see? How if I had the positive side of the voltage up there, I had the equivalent current source going up. So it's very important to keep that in mind. And so similarly here, I have a current source pointing up. I have a Thévenin voltage like that. So that's one box that I have replaced. And then the other box, similarly, I'll end up with a 1 ohm resistor and a 1 amp times 1 ohm voltage. So it will be something like this. A 1 ohm and 1 volt. And then the rest of it. So this is basically my first box, and this is my second box. And notice the direction again. I had this 1 amp pointing to the left, so I ended up with the positive side of the Thévenin voltage on the left. For this box to be equivalent to that box. If I do it the other way, the two boxes are not equivalent. The direction of the current is reversed. You have physically altered something that will make it so that the boxes are not equivalent from the outside. Okay, well, you're now down to a circuit that only has one loop. And actually, the numbers worked out pretty nicely, it turns out, I think. Well, easy enough anyway. So what is this current? So now you can write a simple KVL and get the current there. Right? And that will give you is it minus 4 amps? Double check. Okay. I didn't want to write the KVL and stuff, just did it quickly. Okay. But so I hope you agree with me that if you look at this exercise, the steps we took, going from this to this, and then to this and that, it was maybe a little easier and more pleasant than writing, all the KVLs and KCLs there and coming up with a system of equations. Now, this worked if you wanted something that was outside all the parts that we converted. Okay? Of course, if I was interested in the voltage, let's say across the 1 amp current source, or if I was interested in the current of the 2 ohm resistor on the top left, then where is that? In this equivalent circuit, how do I find out what the current of the 2 ohm resistor of the original circuit is? I won't know directly, right? I could, of course, use the information that I have now to start working backwards and reconstruct my original circuit and propagate what I know backwards. Okay, so you can do things like that. But primarily, what's of interest is, again, when you're looking at something from the outside. Right? And so with these steps of turning, it's a little bit of magic, you might say, turning this initial Thévenin-like circuit to a Norton equivalent allowed us to combine these resistors and then turn that back into a Thévenin later, and also turn the top one into a Tavern, and all of a sudden the circuit became one loop. So the point is, the 10-volt resistor does not see any difference between the circuit we have down here and what was up here. As far as the 10-volt source, did I say 10-volt resistor? 10 volt source, as long as the 10 volt source is concerned, as far as the 10 volt source is concerned, all it sees is the same thing connected to it. So does it matter what I do first? Yes and no, depends on what. So if you look at the top part of the circuit, the 1 ohm and the 1 amp, you could have converted that in the first step, right? But if you look at this part, you see the only thing that you could start with is the 6 volt and 2 ohm that are in series. I see. If these I put in a different order, so if I flip this 1 volt and this 1 ohm, the answer is no. And you can see that also from here. So if I change the order of V Thévenin and R Thévenin, it doesn't matter, because ultimately this will be involved in a KVL wherever it's connected. And in the KVL, you have a bunch of terms adding to each other, and it doesn't matter what order they are appearing in. The direction, of course, matters, the sign, right? And same for the Norton equivalent. So if I had the R on the other side and I here, it wouldn't matter, because the KCL here just is concerned with the addition of all these currents. Yeah, so basically the KVL that I write will have 3 voltage sources in it, and that's exactly what happens before you find your number, right? You're effectively adding those. This is a very important example in terms of giving you insight into what equivalent circuits are and being able to spot chunks in a bigger circuit. Because as you start solving bigger and bigger circuits, ultimately you want to be able to have insight so that you can do design and you can think of what each part is doing. And so recognizing these chunks is important. So I want to move without delay to series and parallel combinations. And again, this is something that I think most of you are quite familiar with. But I remember when I asked last week who could prove, for instance, whether how to combine series or parallel resistors, the degree of comfort went down. So this is our topic. So let me draw an example here. So assume all resistors are R. Find the Thévenin equivalent between points A and B. How would you find the Thévenin equivalent between points A and B? Think about that for a minute. Now, I'm not asking you to use knowledge of series and parallel resistors, but directly find the Thévenin equivalent using the method that we've discussed so far, how to find the Thévenin equivalent. Okay? Well, let's see. If I wanted to follow the, if you want, recipe that we came up with before, I'd say, well, let's start with step 1, find the open circuit voltage, right? Which means between points A and B, I just connect a voltmeter, which means ideally, essentially nothing imposed on the circuit, just a pair of eyes that will tell me what that voltage is between A and B without doing anything else. In other words, this is left open. I just measure or calculate the voltage between A and B. Now, what will that be? 0. Now, you don't need to have a particular piece of information. You can try that. So this is something that you can go write all your KVLs and KCLs, and you will see that all your equations will have no excitation in them. So a bunch of variables with some factors added up together all equal 0. So all of those, the answers will be 0. So you can actually solve the circuit. So you don't need to know this or have the insight or intuition. If in fact you feel uncomfortable with this open circuit voltage being 0, you should do that exercise at home and calculate it. Okay? So you can calculate this using the method of solving circuits, which is KVL, KCL, element relationships. And similarly, you can calculate your short circuit current, which is, well, maybe let's emphasize that that would be when you put a line there. Okay, so that would be your second piece of data, the short circuit current. And again, you can calculate if you're uncomfortable in the same manner. Notice that this is a different circuit compared to the one that did not have this wire. Okay, so you have the open circuit voltage, which is 0, and the short circuit current, which is 0. And so the next question then is the Thévenin resistance, which is supposed to be, so this is your Thévenin voltage, right? And this is supposed to be your Thévenin voltage divided by Thévenin current. Look up here. The short circuit current is the, Thévenin voltage divided by Thévenin resistance. Right? Now, this is 0 by 0, which is what? It can be anything, right? So we have to find something else. And again, on that graph, what happened is that your line was shifted such that the open circuit voltage was 0 and the short circuit current was 0. So those 2 points fell on the origin, and so effectively you have just 1 point in the two of them. And so you don't know the slope. So what should we do? Yeah, so, well, if you're trying to find the slope of this line, and you have already found out that it goes through the origin, but you don't know where another point is, well, try to find another point on the line, right? Literally. So you need to find a point that is not the origin. So far you're here. On the characteristics, you have something like this. So this is both the open circuit voltage and short circuit current. But what's the slope? Well, I don't know. Let's find another point. Right? You need to find another point. And that point can be any point. It's a straight line, so any point. Positive current or negative current. positive voltage, negative voltage, doesn't matter. So you have to find one more point. And so here's what you do. You want a non-zero point. So you apply a voltage, let's say a value V here, and calculate the current I, or something of that nature. Right? So I will do this maybe in a different color. So if I want to find the slope, so let's say I'm interested in this point. Let's call this V naught and I naught. I will apply a voltage V naught and calculate the current I naught. Now, what's the direction of that current? Well, let's see. We are looking at finding the Thévenin equivalent of this big circuit, which means let's imagine we put it in a box. Now, my box is going to look a little strange, maybe. Okay. Now I have chosen to define my IV characteristics like this, and this voltage source, this V naught that I've put there, I have already indicated its polarity, right? So the voltage V of that Thévenin circuit is this. Through my choice of V naught, having the polarity that I had up there, and saying V naught is that V in this for this particular data point, I have essentially said that my V was defined like that. Now, what does that say about the way I have defined my Thévenin box and which way the current should be? Yeah, so if you look at our Thévenin circuit up here, I is going from the positive toward the negative side of the V. So same here. So I do indeed have a well-defined direction for the current. Okay. If I had applied my V naught the other way, well, the current would have been the other way. But so this is the kind of thing that can get very tricky. And so staying on top of these directions is very important. So if I put a V naught there, so this is my general V and I, but for a specific data point, I call this V naught, and that current, so V is V naught in this case, and I is I naught. So here we have a question, wouldn't the current be the other way? Now, in reality, if this V naught was a positive number, and if I calculated what's happening in the circuit, with this convention of current, I would get a negative number, which means the current is actually going in the other direction, right? But that doesn't matter. What's important for me is to stay consistent with my convention here. Because look, if I want to calculate the slope of this curve to get the resistance, well, if V naught is a positive value, is I naught supposed to be positive or negative? Right? The way I've defined it, it will be negative. If you define it the other way, then it's as if you have reversed the convention for this I axis. Okay. It can be very confusing, and it does become confusing. So every time you practice something like this, please think about this very specific point. Go back to a simple Thévenin circuit, look at the directions, draw the IV characteristics, and pay attention to the directions, because you really need to get used to this. All right, so, well, now, what should the value of V naught and I naught be? V naught can be anything, and I naught will be proportional to that. And how do I calculate R from here? Well, simple. The curve for this is simply V equals V Thévenin minus R Thévenin I, right? If I wanted to write the equation for this. Right, you see if I equals 0, I get V Thévenin. If V Thévenin, if V is 0, I get I equal V Thévenin by R Thévenin. So that's just the equation for that line. And same here, you can write the equation for the line. Right? If I is 0, I get Rn In. If V is 0, I get In. So for that specific case, and you see this goes back to the question that we had. You see the way I have defined these directions, I have negative R Thévenin or negative R Norton in the equation. In this particular case, because it's going through the origin, the equation is simply V equals 0 minus R Norton or R Thévenin I. And so for a specific case, for instance, for the specific point, of V naught I naught, then I can say V naught equals minus R Thévenin I naught. Okay, so this is how you would do this. Now you have your Thévenin equivalent. V Thévenin is 0, R Thévenin is that slope. And again, because I have stayed consistent with everything, if I actually do this, if I apply a positive voltage here, I'll get a negative current I naught, and the ratio times a minus sign will give me a positive resistance, as you would expect for this circuit. Okay. So this is the concept of equivalent resistance. You can think of it as a special case of a Thévenin circuit without any source. So you can think of this as a Thévenin voltage without a source, or for that matter, as a Norton current, Norton circuit without a current source, or with a current of 0. Okay. Now you might say, well, if I am simply concerned with the equivalent resistance, I don't necessarily need to conform to the Thévenin convention of signs. I can just apply a voltage, measure the current the other way, and that way I wouldn't have the negative sign. So that's perfectly fine, right? So to summarize this, is simply the Thévenin or Norton equivalent. But very typically, you deal with a circuit which doesn't have any source, and so its Thévenin voltage is 0, or its Norton current is 0. It just has the resistor. Okay. So often enough, we deal. I'm not saying necessarily always, right? Obviously. But very often one might find oneself in a situation where one wants to find the equivalent resistance of a circuit that doesn't have any source. So V Thévenin ends up being 0, or I Norton ends up being 0. You just have a resistor. And that's the equivalent resistance of the circuit. So if you wanted to think of this as a method, or to think of coming up with a method to calculate the equivalent resistance of a circuit that does not have any source, just apply a voltage and measure the current and divide the two, paying particular attention to the directions, right? So we'll turn this around. If you have a circuit with no independent source, okay? So it can still have dependent sources. Those will not create an excitation. They are really just functional dependencies. As long as they're linear, again, all these things that we've discussed apply. And so if you have a circuit with no independent sources, so if you have something like this with many resistors and dependent sources inside, and you want the equivalent resistance, apply a voltage and calculate, the current and divide the two. Paying particular attention to the direction. So in this case, for instance, I would just do something like this. So if I apply a voltage V naught here, if I use this current, like we did in the previous example, then our equivalent will be minus V naught by I naught. This is exactly what we did in the previous example. We were looking at our equivalent between the points A and B. Now the circuit was facing the other way, but that was really just the drawing aspect. And I'm intentionally going back and forth between these different directions to show that there is no particular emphasis on the actual way you draw it on a paper. Okay. But you might say, if I was just interested in finding the resistance, who likes to have an additional negative sign to take care of later? So why not then do it this way? If I do this, then I don't need the negative sign. Okay. So basically, I have applied a voltage source there, or connected a voltage source there, solved the circuit, and you see there's no problem in having some dependent sources there. Solve the circuits. The ratio of these two currents is the resistance. Okay, let's take a 5-minute break. So I want to now specifically look at some specific cases of equivalent resistance. So specific examples of equivalent resistance, but very key and important ones. So resistors in series. So if I have a few resistors, let's maybe draw it like this. R1, R2, till R sub n. And if I'm interested in the equivalent resistance here, well, I'll do just that. I'll apply a voltage and measure or calculate the current there. And if I apply a voltage V naught, and if I'm interested in that current, so if I do this, let me just draw the full thing. So and if I look for this current, so that I don't have a negative to deal with, what will I get? Well, it's a one-loop circuit, right? 1 kVL. And I think we've done enough examples of this to see that if you have V naught, I naught will simply end up being, if you do your KVL, KCL, well, the KCL is really implied in the fact that all these resistors have the same current. So resistors in series, meaning there is nothing branching off between them, so they all have the same current. Okay? You might say that's the definition of being in series. So if I apply my KVL here and do a little bit of manipulation, I'll get I naught equals V naught divided by the sum of all these resistances. And so I can then immediately extract the equivalent resistance from that. This is just a proof for that. That if you have a number of resistors in series, the equivalent of this combination is simply the sum of all the resistors. Now recall that this concept is of limited applicability, because if your circuit wasn't only resistors but also had some dependent sources, then you would actually need to put a voltage source there, calculate the current, divide the two, right? But if you only have resistors in series with nothing branching off, so that they all share the same current by KCL, then this is, you might say, something that you don't even have to memorize, right? It's something that hopefully you will be comfortable using. So this is the proof. Resistors in parallel meaning that they all have the same voltage. So it looks like this. If you're looking here, well, again, do the same exercise. Put a voltage source here. measure or calculate this current. And recognizing that they all have the same voltage, you have already implied all the KVLs here in all these loops. And so all you have left to apply is a KCL that says the current I naught going in is the sum of all the currents going through these resistors. And so if you write that KCL, again, with a little bit of manipulation, you will get I naught being the sum of all those currents. And you see that the voltage across each resistor is V naught. So those currents are just V naught by R1 plus V naught by R2. Right? Or the more familiar form that you have seen. So that's resistors in parallel. They all have the same voltage. You see, on each of these branches, there is only that resistor. So there is nothing else to take that voltage or part of it. Now, I had a question during the break. For this exercise that we did here, if we use this notion of adding series resistors or the inverses of parallel resistors and try to simplify the circuit that way, would we get the same answer as what we would get from this general approach? And the answer is yes, exactly so. So a circuit like that, you would start by identifying where you would see, you would find a series combination or a parallel combination. And so you see here, for instance, down here that these two are in series because there's nothing else branching off between them. So the combination of these two, as far as the outside world is concerned, beyond what's between them, is just R plus R, 2R. And then that combination is in parallel with this other R, so you can get that combination. And then here you have these two R's in parallel, so that will give you R over 2. And then that is in series with this other R with this other R. So it gets simplified that way by adding those up. And then these two are in parallel. So that will give you R over 2. Adds up to this R. And then that combination is in parallel with the combination of these. And then the whole thing is in series with that R, in series with this combination, and they add up like that. And I believe you've seen exercises like this before. I'll also give you some examples in the assignments. But that's going to give you exactly what you get from this general approach, because the notion of combining resistors in series or parallel using these formulas really came from that general approach as a special example of that general approach. Okay. But again, remember that finding equivalent resistance is not limited to a circuit that has only resistors. It could also have dependent sources. And in general, it could also have independent sources, in which case the circuit can be represented not with only a resistor, but a resistor either in series with a voltage source, so that would be the Thévenin equivalent, or in parallel with a current source, that would be a Norton equivalent. Okay. I want to talk now about this concept of voltage division and current division. So this is the simplest example. If you have two resistors like this, across the series combination of which you apply a voltage, let's call this Vs. If this is R1 and this is R2, and if I ask for V1 and V2, well, you can simply solve this circuit and you get the current, which is Vs divided by R1 plus R2, and then multiplied by R1 will give you V1, and multiplied by R2 will give you V2. Okay, so very simple circuit to solve. And thinking of it from the equivalent resistance point of view, you can say calculating I should be very easy because I have two resistors in series. As far as outside is concerned, outside those two, they just add up. So I is simply Vs divided by that combination. And so V1, which is R1 I1, is that, and V2, which is, R1I, because I just had the same current there. Now, what is the sum of V1 and V2? Vs, and that's good, right? Because you don't want to lose your KVL there. Right? So you see that the voltage V is divided between the two resistors in a manner proportionate to their resistances. Whichever has a larger resistance gets a larger portion of that voltage in that KVL. Similarly, there is current division. Let's say if you have a current source, whose current is going to be shared between two resistors, R1 and R2. So this one's going to have I1. This one's going to have I2. Well, they all have the same voltage. Let's call this V. And you could say by definition of equivalent resistance, this voltage is simply this current, Is, times the equivalent resistance. Or the equivalent resistance is V by Is. Now, the equivalent resistance, or equivalent, is just the inverse of the inverses of these two added up. So V is simply Is times 1 over . So this is just the equivalent resistance. Okay. So from there you get I1, which is V divided by R1, right? Which, if you do the manipulation, will give you, right? Because that is just R1, R2 by R1 plus R2. If you divide it by R1, you're left with R2 times Is and I2 . I'm going through these quickly because there's no new concept here, really. You can just think of these as examples that you can solve on your own. But I want to make sure for completeness that we have done them. So you see that if you have two resistors sharing the total of the current of a current source, or another branch for that matter, then of course the sum of the two will be that current, Is, but they share it in a manner proportional to the inverse of their resistances, or the smaller resistor gets a bigger part of the current because the two resistors have the same voltage across. So it's called current division. And again, these are maybe small techniques that will come very handy. Again, as you start analyzing circuits with more complex geometries and with electronic components, these are things that you want to have really developed an intuition for so that you can apply them very quickly. So we have time for one more topic. Take this circuit. Assume you know R1. Find Rx so that the power delivered to it is maximized. So you know Vs, you know R1. These are parameters of the problem. Rx is a variable resistor. So you want to choose its value so that when you put it in the circuit, it absorbs the maximum possible amount of power. Can you guys try that? Well, let's see how would I do that. Well, just calculate the power and maximize it. Now, the way to do that is to calculate the power, you need the voltage and current of that resistor, and you can do that by writing your KVL and solving the circuit. But now that we have more of these techniques, more of these tools, I can maybe do that more quickly. So if I'm interested in this V and I, well, I know is simply that Vs divided by the equivalent resistance, which is the sum of those two. And V, I can write it maybe using voltage division. Again, I don't have to use any of these formulas, but I can. So if I'm interested in power, and if you want to maximize this, with respect to the variable Rx, so you're trying to change the value of Rx to maximize P, I'll take the derivative with respect to Rx. Set this equal to 0. And that would give you the point of maximum. Has anyone done it? What's the answer? So from that, do at home, or if you haven't done it yet, or if you have difficulty, come see me. But it's a little bit of manipulation here, and you will get Rx equal R1. So if you choose a resistor whose value is equal to that R1, you will get the maximum amount of power delivered to it. It doesn't mean you're getting the maximum amount of voltage, right? To get a higher and higher and higher voltage, you would just want to increase Rx. The bigger Rx, the bigger its voltage, right? If you wanted to maximize current, you would just make Rx smaller and smaller. But if you want to maximize the product of the two, that's an optimization problem. And you will see from this little example, this is again an example. It's not that the two have to be equal. Yes, so derivative equal to 0 could give you minimum or maximum. So prove that it's maximum. You can look at the second derivative, right, to see if it's a point of minimum or maximum power transfer. Now, this is, you might say this is a very small problem, and it looks like something maybe with limited scope. But it's actually an example of a much broader concept that goes beyond circuits. Well, first of all, in the realm of circuits, has anyone heard of the concept of impedance matching? No? You might hear this. If someone is trying to make a transmitter, they will try to make their antenna impedance match to the circuit. Or if you're working with microwave circuits, you will see this connecting instruments, connecting different stages of a circuit. And it's applicable with the general concept of impedance, which is a generalized version of resistance. So if you have inductors and capacitors and you have an AC circuit, you can attribute something that looks like resistance to them, and that quantity is called impedance. And so you want to maximize power transfer in circuits at different frequencies and so on. So you will see a broader version of this with impedance. You will see it more broadly speaking beyond circuits in other systems where, in an acoustic system, for instance, if you want to make a speaker that will deliver a lot of power to the air, you want it to be impedance matched to the air. Now, there we are talking about acoustic impedance. Okay? If you want to have a piece of glass that transmits the maximum amount of light that hits it instead of reflecting it, you want to have their quote-unquote optical impedances matched if you want. Anyone heard of anti-reflection coatings? Basically what you're doing is something very similar there to help maximize the amount of power delivered from one medium to another. And so this is not limited to electrical circuits in DC. It's much broader, the concept of maximum power transfer. So this is why this is an important exercise, even if in this case it's one small example. Okay, so this is profound. Okay. So I think we have to stop it here for today. So we'll continue next time. Thank you.